The EIGRP routing protocol needs a mechanism to determine which path to the destination is best. If there are several possible paths to the destination, we could say that the path selection refers to the method by which the protocol determines the best path. Each EIGRP router maintains a neighbor table. This table includes a list of directly connected EIGRP routers that are formed in adjacency with this router. Neighbor relationships are used to track the statuses of these neighbors. After the neighbor table has been built, each EIGRP router maintains a topology table for each router protocol configuration. The topology table includes route entries for each destination that the router learns from its directly connected EIGRP neighbors. But remember, EIGRP chooses the best route to a destination from the topology table and places only this best route in the routing table. EIGRP uses two parameters to determine the best path to the destination: advertised distance and feasible distance. Router B gets information from router A that network 10.1.1.0/24 is reachable via router A, and the metric to reach this network is 2000. So how was this metric populated? The metric equals the feasible distance for this network. And what is the feasible distance? Feasible distance is the sum of the advertised distance learned from router A and the EIGRP metric for router A to reach router B. As you can see, the advertised distance in this example equals 1000. This is the metric that router A uses to reach the network 10.1.1.0/24. To calculate the feasible distance, you need to add the metric for router A to reach the neighboring router B. This equals 1000 as well. Finally, you may calculate the feasible distance on router B for network 10.1.1.0/24. The final result is 2000. This is the metric for the network 10.1.1.0/24 from the perspective of router B. A router configured for EIGRP compares all feasible distances to reach a specific network and then selects the lowest feasible distance and places it in the routing table. The feasible distance for the chosen route becomes the EIGRP routing metric to reach this network in the routing table. The EIGRP topology database contains all the routes that are known to each EIGRP neighbor. As you can see in this example, routers A and C sent their routing tables to router B, whose table is displayed. Both routers A and C have routes to network 10.1.1.0/24. So router B has two entries to reach 10.1.1.0/24 in its topology table. The EIGRP metric for router B to reach these routers A and C is 1000. Add this metric to the respective AD for each router, and the results represent the FDs that router B must travel to reach network 10.1.1.0/24. Advertised distance for router C in the example is 1500, while the AD for router A is 1000. Router B chooses the smallest FD, that's 2000, and installs it in the IP routing table as the best route to reach 10.1.1.0/24. The best path from router B to reach network 10.1.1.0/24 is via router A because of the lower metric. The route with the smallest FD that is installed in the routing table is called the successor route. Router B then chooses a backup route to the successor that's called a feasible successor route if one or more feasible successor routes exist. We have backup or feasible routes via router C in this example. You could ask yourself, what happens if the route via the successor or router A becomes invalid? There are several reasons why this could happen. Possibly because of a topology change, or if a neighbor changes the metric. In this case, Dual checks for feasible successors to the destination route. If a feasible successor is found, which is router C in this example, Dual uses it. With that, it avoids the need to recompute the route. EIGRP guarantees rapid convergence this way. If no feasible successor exists, recomputation must occur to determine the new successor.